this video, I want to take a look at an example problem where we attempt to calculate the momentum of a falling object, which is falling and sliding at the same time. So in the drawing here we have a, let's call it a ladder resting against a wall, but it's slipped and the ladder has started falling such that the top of the ladder against the wall is falling at 2 meters per second. At the instant that we're looking at it, the orientation of the ladder is 30 degrees off the horizontal. It's 4 meters in length, and we're going to assume that the center of gravity is located right in the middle. So to start analyzing this problem, we're going to pull that ladder out so that we can kind of look at it by itself. And probably the easiest way to do this is going to first be to locate the instantaneous center for this moving object. So a few things that we know. We know that because of the constraints of the environment, the top of the ladder is moving downward, and corresponding to that, the bottom of the ladder can only be moving straight to the left. So what this does for us is it allows us to locate the instantaneous center, because we know that at any instant in time, depending on what the velocities of any point on the ladder must be perpendicular to a line that passes through the instantaneous center. So if I draw a line perpendicular to this velocity and draw a line perpendicular to this velocity, I can locate the instantaneous center out here at the intersection. And kind of completing some setup here, we know that this angle is 30 degrees because it corresponds to the bottom angle down here, which we had given. And our center of gravity is somewhere in here. And if I think about how this is all moving, the center of gravity at this point in time must also be moving with a velocity vector perpendicular to the line that passes through the instantaneous center. So we get a velocity that looks like that. Now, if we think about how this instantaneous center moves as the ladder slides down, we can realize that this angle here must also be 30 degrees. And therefore, we can see that this is 30 degrees. And so forth. So based on all of that, we can calculate some various lengths. We know that this distance between the instantaneous center and G is 2 meters if the length of the ladder is 4 meters. And we can also use our geometry to find the length of this side over here as 4 meters times the cosine of 30. All right, so we've got a lot of geometry figured out now. Now we can actually start calculating some of the things we're actually looking for. So first, we might want to know what the angular velocity of our ladder is. And the angular velocity we can draw on here as about the instantaneous center. Whenever we have an object moving with this kind of general planar motion, we know that it's always it can always be approximated as rotating via fixed axis rotation about its instantaneous center. So we can draw that way. Then we just need to know a relationship between velocity and some length in order to calculate that. Well, luckily we know the velocity over here is 2 meters per second. That was given. And we just calculated the length of this top line as 4 meters cosine 30. So we can go ahead and plug those in. And from that, we would get that the rotational velocity, something like this, in radians per second. All right. Next, we can use that if we were looking for to calculate Vg, which is the velocity of the center of gravity. We already have its orientation, but we haven't figured out its magnitude. And we can just basically restructure this equation we just used as omega r, but now plugging in our new omega, because that's the same everywhere, and multiplying it by the distance that we figured out here between the center of gravity and the instantaneous center of 2 meters. So that gives us that the center of gravity of the ladder is falling down and to the left at a rate of 1.155 meters per second. All right, so if we put all this together, we're going to start by calculating the angular momentum around the center of gravity. And we have from before that this is equal to Ig omega, so mass moment of inertia around the center of gravity. And we're going to treat this as kind of just a long, slender rod. Would be a good approximation for a ladder. And as such, our equation is 1/12 ml squared. So that's mass, 1/12 mass times length squared. So we'll plug in 1/12 times the mass times the length squared. And omega that we calculated. So this gives us 3.85 kilogram meters squared per second. All right. Next, we want to calculate the angular momentum around the instantaneous center. So this should be different because we're rotating around a different angular position for this momentum, and because it's at a distance from the center of gravity, that's going to change what's happening there. So one of the ways that we can express this is as the mass moment of inertia around the center of gravity times omega, as we just did. But now because we're talking about an axis that's different from the center of gravity, we need to add on the fact that the center of gravity itself is moving. So we'll take the distance between those two, the instantaneous center and the center of gravity, and multiply that times the linear inertia of the center of gravity. Luckily, we just calculated Ig omega, so we can plug that in. Distance that we found was 2 meters, mass, and velocity. And this gives us 15.4 kilogram meters squared per second. So we can see that we might have a much higher angular momentum when we're talking about the instantaneous center because it's located again at some distance from that center of gravity. Now you may recall that we had another mechanism that we could use for calculating this same value, the angular momentum around the instantaneous center, which we found ends up being really the same thing, but expressed in a slightly different way. So we take the mass moment of inertia around the instantaneous center and multiply that times omega. So to do this, we need to remember that usually we have the equation for the mass moment of inertia around the center of gravity. That's usually what we would find, like in the back of a textbook. But we can adjust that using parallel axis theorem. And doing so, we would get the same equation again, 1/12 times 5 times 4 squared, plus parallel axis theorem is md squared, so mass times distance squared And what we find is that that looks very similar to what we did before, at least in terms of how it's expressed. And then we would multiply that by the angular velocity. Doing so, we get the same answer that we got above. All right, thank you.